Hello, today our study topic is the case study on BEAM implemented project in Hong Kong. The main stadium of Kai Tak Sports Park is chosen as our case study. Here is the flow of our presentation. So why we choose the main stadium to be our case study? Actually, the technical circular of 2017 regulates that the project amount estimated at 30 million Hong Kong dollars or above shall adopt BRM, and the project amount of our project is almost 13 billion Hong Kong dollars. Also, it has a complex design which is shaped as three-tier infinity bowl. Rivet and Navar's work are considered as the crucial technologies in the design stage.
In the construction of the main stadium of Kai Tak Sports Park, BEAM is adopted throughout the project's life cycle, from initial design stage to construction stage. Using the BEAM software, Revit and Navisworks, the scope of BEAM use includes 3D visualization, analysis on wind loads, structural loading and sustainable development, MEP coordination, and clash detection, as well as 4D construction simulation of the construction process.
Moving to the BEAM application in the project, Arab, as the main contractor, takes the advantages of Revit to create 3D architectural drawings, simulate the wind nodes on the building, carried out foundation design, and MEP coordination to facilitate a smooth construction in the future. For the wind analysis, as the initial Revit model was built, it is used to study the wind climate under different circumstances of wind node. For example, as shown in the left-hand figure, it is predicted that there would be uplift and down forces on the leeward canopy due to the effect of wind pressures on the upper and lower surfaces of the roof. Therefore, the model was used to carry out the distribution of wind pressures in the building structure, which is shown in the right-hand figure for the distribution of wind pressure at different times and directions. So, with the aid of wind analysis, it can facilitate the design of foundation system to resist the electrical and other building loads. At the initial stage, in order to resist the imposed loadings and meet the employee's requirement, there are three options of foundation designs, which are large diameter block piles, rock-socketed steel edge piles, and driven steel edge piles. After considering the allowable loading capacity, construction time, and wind forces, the project team decides to use large diameter block piles and socket edge piles, as shown in the above figures. With the use of Revit, the 2D drawings can simultaneously generate the 3D model of the foundation, which facilitates further analysis and better visualization. Also, as BEAM is an object-based tool, different specifications or parameters can be added to the object. This not only facilitates structural analysis, but also enables convenience to the project team for modifications due to the project variations. As shown in the above figures, we can clearly reveal the object properties such as unit weight, damping ratio, and loading strength. For MEP coordination, the Revit model is also used to identify clashes, prevent rework, and facilitate the prefabrication of building elements. For example, to coordinate the E&M work, trunkings, and ICT equipment. As shown in the above figures, the MEP errors can be identified that the trunkings for electrical work are not connected at one side of the building. This figure shows the section of the stadium. We can see that there are lots of clashes in the model. Different trade teams can be notified of these errors and coordinate for changes in the design. On the adoption of Navisworks, it is used to facilitate clash detection and the construction simulation for site and construction work arrangement. With the aid of the Revit model, it can be imported into the Navisworks to conduct clash detection to track down errors before actual construction to improve work quality and lower costs. There are three types of clashes, which are hard clash, soft clash, and workflow clash. The workflow clash means that the collision in construction workflow, for example, the incorrect installation time of equipment and the product delivery time. For the hard clash in the project, it means the collision of two objects. From the clash report, one of the examples is the clash between the transom and RC beam. The clash between MEP and architectural model can also be detected by linking these two data planes of model. For the soft clash, it means the geometric tolerance in the building design. For example, there is a requirement for the maintenance and working space of AV equipment, which is shown in the red color in the figure. Therefore, with the above detections, comments can be made on the clashes to show the required amendments. Errors and redundancy of the construction could be avoided before construction to save cost and time while enhancing the project quality. For the 4D simulation, this can be achieved by the combination of levels work file and the master plan. The master plan can be created by defining different work packages and milestone events by the use of MS Project. The adoption of 4D simulation in the project allows the project team to simulate and analyze the arrangement of site equipment, such as optimizing the use of tile cranes by calculating the turning radius, and the working location and workflow of trucks during the excavation stage. This can help achieve a better resource allocation to reduce construction costs. In addition, the simulation can also show the construction condition during different construction stages. For example, the different color can be used to show the specified construction condition, like yellow represent the temporary work and blue represent the precast work. Therefore, the 4D simulation not only allows a better understanding and visualization of the project, but also enhances the resources allocation and to minimize costs while maximizing efficiency at the early stage of construction.
As for the benefits of adoption Revit in our case, it provides a 3D simulation of the building. It's very important in a complex design structure like our case. Moreover, as to achieve the high connectivity with other surrounding facilities, the subpodium, as located below the existing ground level, is proposed. The complex design and leakage system imply the consistent modification and collaboration of different departments. However, it may obtain satisfactory performance of dealing such problems by using Revit due to its 3D visualization and built-in collaborative nature. Another benefit is that Revit can facilitate the accurate wind analysis. Its feature of 3D simulation may help to grab the picture of whole structure of different roof conditions. It may also facilitate the progress of investigating pressure coefficients based on the two positions separately. In addition, due to the retractable roof design, some data of dynamic properties describing the nature of frequency shall be collected. Regarding the benefits of using Navar's work, it will be the collaboration of the proposed design. The feature of clash detection is to forecast the error of the design, and the clash can be eliminated by amending the design in advance. It also implies a risk reduction in terms of money and time. In the subjected project, it adopted Navar's work in the construction the main stadium for 4D simulation of the actual building progress. It benefits the project manager to arrange the site activities and allocate the resources. In the study case, the bowl of the main stadium consists of two construction methods, including in situ reinforced concrete for ranking beams and precast reinforced concrete for seating tiers. It may achieve desirable performance in allocating the resources and arranging the activities by using Navar's work.
Despite the benefits, there are some limitations of BIM application hindering its adoption into practice within the industry. First, there is lack of data interoperability in BIM software. Data interoperability is imperative as it allows multiple project stakeholders to collaborate as project information is updated. However, BIM is not interoperable with other software. It cannot keep the data intact when exchanging information among different computer platforms as it was not typically designed to share data with other programs. Hence, fluent information interchange among project stakeholders cannot be attained. Secondly, BIM application may create some legal concerns, such as the BIM model editing authority and product liability risks. As multiple stakeholders are constantly developing and editing the model during the project, it is difficult to determine whether the contractor or designer should be liable for any defects in the BIM model. Also, there is lack of contractual arrangements to protect the private data of BIM model from loss and misuse. The adoption of BIM requires high implementation fee, including cost of software and competent quality hardware, hiring BIM experts or training of employees. Although long-term savings can be achieved, the initial cost is high. Besides, there is still a low frequency of BIM usage in construction projects, and hence a concern in overall cost effectiveness. Therefore, small and medium-sized businesses may lack the resources and desire to implement BIM fully.
Let's focus on the recommendations now. Traditional information sharing may be cumbrous and inefficient, hindering the exchange of data and information as well as generating paradoxes on the liabilities and proprietaries. Common data environment as one of the recommendations for better BIM use is a single source of the information which aims to facilitate freely sharing project data among different project participants. Common data environments is capable of fostering easy exchange of models and data and spatial coordination, while adopting a centralized model with coherent and equalized system between each composing model. Different teams could generate, share, and access information via an explicit data structure and common file naming convention. Also, any amount of documents could be created from various combinations of model files. Hence, it could be alleviate the problem of data interoperability. Another value added to alleviate problem is that the ownership of data is also clarified to prevent from the ambiguous liability and proprietary since the original creator possessed the ownership of the information and the authority to revise it. It signifies that the original creator's liabilities will rarely be altered in spite of the incorporation of their model into the synergetic model. Under the structure of the BIM addendum, namely a standardized contract document, a license enabling reproducing, distributing, displaying, or using a model from a party for the single purpose of the project will be upward and downward offered to all project participants. Furthermore, the BIM addendum could identify that a party like the contractor or subcontractor, apart from design experts, might possess the intellectual property rights and the project. There are financial grants of 1 billion Hong Kong dollars for construction innovation and technology funds. Supports related to BIM like BIM software and computer BIM training courses have taken up a significant portion in the scope of funding. The time of application was vastly shortened thanks to the easy and concise application procedures and pre-approved lists. It could be seen that applying for this fund is a feasible channel for the small and medium-sized companies to enhance the adoption rates of BIM. The BIM project of the main stadium of Kai Tak Sports Park was selected to conduct this focus study to conclude a series of BIM applications in this project, including adopting Revit and Navisworks have been illustrated. Benefits of these applications, including creation of simulation accuracy of wind analysis, have been presented accordingly. However, some limitations like data interoperability have emerged. Hence, some recommendations like introducing common data environment have been made. Various information and knowledges have been soaked up after this focus study. It's believed that it will be conducive to create an insight on how to propel the future development of BIM. This is the reference list. Thank you for listening.